Today I'm going to talk about infinite sequences and series. An infinite sequence is a sequence that continues on forever. Remember, a sequence ordered set of terms. We'll say ordered set of numbers. An infinite sequence converges, vocabulary word, if a sub n approaches a constant as n goes to infinity. A sub n goes to one single number. Those elements in your sequence, they're going to start converging onto a single value as n gets really big. Let's determine if the following sequences converge or diverge. So it either converges or diverges for your sequence. My first example, a sub n equals -2 to the n. I find the easiest thing to do is write out, well, okay, I said it's easiest. I'm going to do it on the first one, but not the second one, sorry. So for the first one, we're going to write out the first couple of terms and see if we see a pattern. So n equals 1 gives me -2. N equals 2. -2 quantity squared is +4. N equals 3 would be -8, +16. You can imagine this, right, plopping back and forth between positive and negative, but getting really big. I'm going to do ... keeps on going. This one diverges. It does not approach anything nice. One thing I've seen happen is you can plot your terms and see if they head towards something. So n on the x-axis, the horizontal axis, a sub n on the y-axis, then we'll have n equals 1, n equals 2, n equals 3, etc. So n equals 1, I'm down here at -2, n equals 2, I'm up here at 4, n equals 3, I'm down at -8. So my terms are not headed towards any one particular number. Example 2, a sub n equals 3n squared plus 2n minus 8 all over 5n squared plus 6. Again, we're letting n get big. Think about rational functions. And when we looked at what happens as n gets big, this was what your horizontal asymptote approached. As n gets big, it's those leading terms that start calling the shots. I don't want to start writing those out because they aren't going to look like 3/5 anytime soon, or anything that I'm going to recognize as 3/5 anytime soon. But I know from my algebra life that as n gets big, those a sub n's will start approaching the ratio of those leading coefficients because the degrees were the same. This one does converge. The terms will all start looking like 3/5. We can also have an infinite series. So this is a series. We'll have our series, right, summation notation of those a sub n's. N's going to start at 1 or some fixed number, but it's going to go on forever to infinity. We'll talk about partial sums of infinite series. A partial sum is the sum of the first n terms. If we're talking about a partial sum, we say s sub n. Example, find s sub 8 for the infinite series k plus 1 squared as k goes from 1 to infinity. So that'll be 4 plus 9, k is 2. I'm going up to 8, so I'm going to write out the first 8 terms. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared. stop at 9 because that's 8 plus 1. All of these together is s sub 8. Well, I don't really want to add those, and I remember my summation formula. It's not exactly what I need, but we're gonna figure this out. The sum of the squares from k equals 1 to n, right, it has a formula we can use. N times n plus 1 times 2n plus 1 all over 6. Let's see, if I did this, if I take what I have, let me grab a different color. I have a different color here. To take what I have that I'm supposed to find the sum of, I know by the time I'm done, we could have just punched it in the calculator. I get it, I hear you, but I want to do it nicely. If I do a 1 plus and pretend, then I'm adding up the k squareds from 1 to 9. That would be this. What I need is that, but I just have an extra 1. I'm going to find this, the sum of the k squareds from 1 to 9, get that sum using my formula, and then subtract 1. Okay, my formula says that would be 9 times 10 times 18, 19, all over 6. Doesn't go in evenly, but I can get rid of the 6. I take the 2, gives me a 5. I'll take the 3, gives me a 3. That's going to be 15 times 19. $285, but I had an extra 1 in there, so the sum is 284. Anybody who went ahead and just added those up because you got tired of waiting for me, I hope I got it right. Okay. Now, we might have an infinite series, the whole infinite. We're going to add up all infinite numbers. It may converge. Now, if it does converge, then a sub n has to go to 0 as a sub n gets big. But just because a sub n goes to 0 as n gets big, that's not sufficient to say that the series converges. So, an infinite series may converge if a sub n goes to 0 as n gets big, but it also might not. So a sub n going to 0 is a necessary condition, but not sufficient. So there's a very common example that you'll catch at the harmonic series. Harmonic, I can write, series diverges even though a sub n goes to 0. And the harmonic series is 1 plus 1/2 plus 1/3 plus 1/4 plus dot, dot, dot. Okay. So my a sub n's are going to 0, but this series actually, this infinite series doesn't converge. I know, interesting. Just a little aside that you will come across later in your math lives. For now, we'll talk about an infinite geometric series. If that common ratio, or the absolute value of it, is less than 1, it does converge. And the formula is a sub 1 times 1 minus nope, I was starting to write the one for a finite series. The formula for the infinite series is a over 1 minus r, and a is that first term. R is our constant ratio. Let's do some examples. Find the sums. So adding from 1 to infinity of 1/3 to the k. Write out a couple of terms just to see. 1/3 plus 1/9 plus 1/27 plus all of those terms. If we keep adding those up, they converge to, right, a number. And that number is S equals my first term divided by 1 minus R, so 1 minus 1/3. So 1/3 over 2/3. Flip and multiply. So that sum is, the infinite sum is 1/2. How about the next one? This one, it's not written in summation notation, but can we find that common ratio? What is R? What do I multiply each subsequent term by to get the next one? 1 times what to get negative 1/2? That first one is negative 1/2. Does that hold? Negative 1/2 times negative 1/2, positive 1/4, times negative 1/2, positive, or 1/4 times negative 1/2, negative 1/8. Absolutely. Can you write the next term just to make sure? The next term in our series would be plus 1/16 minus 1/32 plus dot dot dot. So my ratio is negative 1/2. My first term is 1. Therefore, my sum is 1 over 1 minus negative 1/2. 1 over 1 plus 1/2. 1 over 3/2. 2/3. Telescoping series. A telescoping series is an infinite series where most of the terms cancel out. We're going to write out the first few terms, find the sums. So I'm adding from 1 to infinity, 1 over n minus 1 over n plus 1. Let's write out our first couple of terms. N equals 1 gives me 1 minus 1/2 plus. So all of that is a sub 1. A sub 2. 1/2 minus 1/3 plus. N equals 3. 1/3 minus 1/4 plus dot dot dot. Do you see what's happening there? So I have a negative 1/2 and a positive 1/2. Gone. Negative 1/3, positive 1/3. Gone. Right, all the way out. What's that last term we're going to add on? It's going to be 1 over a really, really, really big number. So 1, right, minus 1 over some really big number. That's what's going to be left. Really big number. And 1 over a really big number is 0. So that telescoping series adds to 1. What happens if your fraction isn't split apart? This time I have 2 over n squared plus 4n plus 3. I'm adding them up from 1 to infinity. Make sure your nth term goes to 0. And it does. Otherwise, it doesn't converge. If your nth term does not go to 0, that's what I should have written on my first page. Let me find that. Back over here. Right here. Oh, no, it was from here. An infinite series is a goes to n. So if a sub n does not go to 0, as n gets big, then the series definitely diverges. Okay, back to this guy here. Partial fractions. We needed a reason to use our partial fractions again. We're going to use those and hopefully find us a telescoping series here. Partial fractions, so we factor the denominator, n plus 3 times n plus 1. I'm ignoring my summation, I'm just doing the partial fraction decomp here. A over n plus 3 plus b over n plus 1. Multiply through by that denominator of n plus 3 times n plus 1 gives us 2 equals, so the n plus 3's cancel on the first one, and I get a times n plus 1. When I multiply that common denominator by my b over n plus 1, the n plus 1's cancel, leaves me b times n plus 3. Figure out what a and b are, so let n equal -1. That tells me 2 equals a times 0 plus b times 2. -1 plus 3 is 2. 2 equals b times 2, so b is 1. Nice. To find a, we'll let, here we go. To find a, we'll let n equal -3. That gets rid of our b there. 2 equals a times -3 plus 1 plus b times 0. 2 equals a times -2. A is -1. Nice. This means I can, I'll grab a different color, rewrite my summation. N goes to 1, or from 1 to infinity, and my fraction can be written as, I'm going to write my positive one first, 1 over n plus 1 minus 1 over n plus 3. Okay, phew. So some initial work, and now we're going to write out a couple of terms. N equal 1 gives me 1/2 minus 1/4. There's our n equal 1. Don't look here. N equal 2. So plus because of the summation. N equals 2, I get plus 1/3 minus 1/5. N equals 3. Plus 1/4 minus 1/6. N equal 4. I need a couple more terms. I don't see it yet. N equal 4. I know some of them are canceling. I just want to make sure everything's going to go away that I think is going to go away. N equal 4. I get 1/5, so plus 1/5 minus 1/8. 4. I know, one more. It's harder for me when they're not right exactly lined up. N equal 5 will give me 1/6 positive minus 1/8. No, that can't be right. Equal 4. N equal 4. Oh yeah, this was 1/7. Thank you. Thank you, those of you who are shouting. N equal 5. Okay, plus ... I guess that's good enough. We're going to have to figure it out here. So I have a positive 1/2. I don't have another 1/2 that's going to get rid of, so I'll keep that. I have a -1/4, a positive 1/4. Those guys are gone. The 1/3, I never came up with a -1/3, so that one's going to stay. I have a positive 1/5 and a negative 1/5. I have a negative 1/6 and a positive 1/6. I think, right, if I get my next term, I should have a positive 1/7 that I can get rid of that one on. So everybody's telescoping in on each other, and I'm left with 1/2 plus 1/3. Oh my gosh, all the way back here, this equals 1/2 plus 1/3, which is 5/6. Oh, if you added up all infinite number of those. Okay, last thing before I go. Trigonometric functions and other ones like e to the x, natural log x, they all have series forms of them. They're called either Maclaurin series or Taylor series or power series. And you can use these to come up with, right, the sine functions. So sine of x is equal to x minus x cubed over 3 factorial. So that exclamation thing is factorial. 3 factorial means 3 times 2 times 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, etc. It's on your calculator under the math menu. Okay, you can find it there. So sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... continues on forever. Call this an alternating series when the terms go positive, negative, positive, negative. Another alternating series. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... Keeps going on forever. A couple things. I don't know if you guys noticed or not, but sine is an odd function. You'll notice all the powers are also odd. Cosine is an even function. All the powers are also even. Can we write these in summation notation? Do you want to give it a shot? Sure. Sine x equals, we're going to add them up. They have an x in them. That's cool. We'll use n, 1 to infinity. We're just odd. To get odd numbers, 2n plus 1 or 2n minus 1, right, to force something to be odd. So if I want to start with a 1, I'm going to use 2n minus 1 to get my odd numbers there. So I have x to the 2n minus 1 divided by 2n minus 1 factorial. Oh, I need to change my signs though. Before I do my changing signs, let's make sure. N equals 1, I'll get 2 minus 1, that's x to the 1st, divided by 1 factorial. N equals 2. Get 4 minus 1, x cubed, 4 minus 1, 3 factorial. Okay, great. So I've got the 3s and the 5s and the 7s. Now I need to change my signs. So that would be, I do that with a negative 1. Should go out in front, but I didn't really leave myself enough room. I'm going to squish it in. Negative 1. But I want my first one to be positive, so that would be to the n plus 1. So my first one would be negative 1 squared, would make that positive 1 in the front. N equals 2. N equals 1. Yes, positive. N equals 2 would be odd. Negative 1 to the 3rd power is negative 1. So that's going to work great. Okay, there's sine, cosine. And from 1 to infinity, oh, that first one, 1 I could think of as 1 times x to the 0 divided by 0 factorial. 0 factorial is just defined to be 1. Just going to put that out there. And x to the 0 is also 1, right? As long as x isn't 0, which will say x isn't 0. Then I would have negative 1. I have to do my alternating thing. Then I could have x to the n. How about x to the 2n? because I need all of those to be positive. And let's start this at 0. Look at me. I'm just going to change it to suit myself. And that means I can make that to the n, and that's a 2n, and then I'm dividing it by quantity 2n factorial. That's one way at least.